Welcome to ArXiv Preprint Server Daily, AI Frontiers, a podcast that delves into the most recent artificial intelligence research. Today's episode hones in on the domain of computer vision. The primary goal of this multidisciplinary field is to endow computers with the capacity to understand and interpret the visual world, much like humans do. Computer vision is a rapidly progressing field with diverse applications. Its main objective is to emulate the human skill of extracting structures from visual data. Today's discussion centers around several key areas: deep learning, data augmentation, integration of multimodal data, and self-supervised learning. One of the key themes in computer vision that emerges from our analysis of 17 papers is the application of deep learning. This subset of machine learning utilizes deep neural networks to model complex patterns. An example is the 3D PyRNet features fusion for spatiotemporal feature learning paper by Ula and colleagues. Their research employs variations of deep learning models such as convolutional neural networks, vision transformers, and graph neural networks. Another significant theme is data augmentation, a technique that makes slight modifications to existing data to enhance model performance. This technique is particularly beneficial when data is scarce. A notable example of this is Cui and team's paper titled MEDIOG, Exploring Visual Augmentation in Medical Imaging. The fusion of multimodal data and the adoption of self-supervised learning are emerging trends in computer vision. The former involves integrating multiple types of data for improved results. For instance, Weber and others' paper, PyVit-Fuse, a foundation model for multi-sensor Earth observation data, presents a model that blends multimodal Earth observation data. In self-supervised learning, models learn from the input data without the need for explicit labels. Upon diving deeper into these papers, some significant findings were noted. Ahmad and colleagues introduced a novel framework for human pose estimation and segmentation in their paper, Visual Cent, Visual Human Analysis Using Dynamic Centroid Representation. This framework surpasses existing methods in both accuracy and real-time performance. Chi and others demonstrated that data augmentation significantly enhances the classification accuracy of medical images in their paper, MEDIOG, Exploring Visual Augmentation in Medical Imaging. Camarul and team present a new pipeline for ship detection in synthetic aperture radar images, delivering exceptional accuracy in their study, R-sparse RCNN, SAR ship detection based on background-aware sparse learnable proposals. Regarding methodology, these papers mainly utilize deep learning, data augmentation, and self-supervised learning techniques. Deep learning involves training large neural networks on extensive data sets. Although successful in many tasks, their performance is reliant on the quality and quantity of data and often requires considerable computational resources. Data augmentation involves creating new training samples by applying transformations such as rotation, scaling, or cropping to the existing data. This can enhance model performance, especially when data is limited. In self-supervised learning, models are trained to predict some parts of the input data from other parts. This eliminates the need for labeled data for training. Taking a closer look at the research paper, 3D PyRNet Features Fusion for Spatiotemporal Feature Learning by Ola et al., it is clear that the application of variations of deep learning models designed to automatically and adaptively learn spatial hierarchies of features represents significant advancements in deep learning applied to computer vision. In the paper MEDIOG, Exploring Visual Augmentation in Medical Imaging by Key et al., a framework for data augmentation in medical imaging is introduced. This research demonstrates a significant improvement in classification accuracy, highlighting the potential of data augmentation in the medical field. The paper R-sparse RCNN, SAR ship detection based on background-aware sparse learnable proposals by Camarul et al., presents a new pipeline for ship detection delivering outstanding accuracy. This paper enhances maritime security through advanced computer vision techniques. As for future directions in computer vision, challenges persist. These include the need for large amounts of labeled data, substantial computational resources, and model generalization. Future focus will be on improving efficiency and scalability of models, developing methods for learning from unlabeled or partially labeled data. The field of computer vision is evolving and expanding rapidly. Despite challenges, the progress made is significant and the potential applications are vast. As research continues, we move closer to our goal of creating machines that can understand and interpret the visual world as well as humans do. Stay tuned for more insights and breakthroughs in upcoming ArXiv Preprint Server Daily AI Frontiers episodes. A quick note about the creation of this slide deck. It was synthesized using AI tools, including the GPT-4 model by OpenAI. Text-to-speech synthesis was performed using OpenAI, and image generation was also done using OpenAI. A human expert reviewed the generated content for accuracy and cohesiveness. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from the ArXiv preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights.